Okay, welcome to the Chapter 3 lecture, Measures of Central Tendency. Okay, and again, the course, or the subject, is by nature inherently cumulative. So things you should know in order to understand the current chapter content, the summation notation from Chapter 1, and you should have a firm grasp on frequency distributions, were covered in Chapter 2. Okay, so what is central tendency? Central tendency is a statistical measure. It's a single score meant to define the center of a distribution. The purpose of a central tendency is to find the single score that is most typical or best represents the entire group. Okay. Most of us are familiar with the term average. So central tendency, in a sense, is basically the average score. But there are a number of different ways to derive this. So here are three histograms, scores along the x-axis, frequency along the y-axis. And these three distributions kind of demonstrate the difficulty of defining the central tendency. Right? In each case, try to locate the center of the distribution. For example, let's look at the top left figure. Well, in this case, clearly, it would seem pretty obvious that 5 would represent the center. Look in the top row, the right figure. Does the central tendency fall at 8? Probably not, even though that's where most of the scores are. Is this a symmetrical distribution, or is it asymmetrical? Is it skewed? And if it's skewed, is it positive or negatively skewed? So where did the central tendency fall for this one in the top right? How about in the bottom right? We might be likely to say that the central tendency would be 5, right? Smack dab in the middle of these two distributions here, but there are no scores there. So this slide presents a good opportunity to think about how the central tendency needs to be characterized dependent upon the type of distribution we're dealing with, right? So different distributions do not necessarily lend themselves to the same measure of central tendency. Another way to say this is to say different distribution shapes require different conceptualizations of what the center actually is. So we need to choose a central tendency measure that best represents the scores in a specific situation. Okay, one form of central tendency with which I'm sure most of you are pretty familiar is the mean. We talked about the mean when we were looking at frequency distribution tables in the previous chapter. The mean is the sum of all the scores divided by the number of scores in the data. And in this case, take particular note of the symbols that are employed. The population mean is represented by that kind of funny looking U. The sample mean is represented by the capital M. And then the formula, we use the sum symbol, right? The sum of all x's, and for population mean, the sum of all x's divided by the number of scores, capital N for number of scores. And then the sample, we've got again the capital M representing sample mean, the sum of all x's, all scores, divided by the number of scores. But in this case, number of scores is represented by the lowercase n. So you want to compare and contrast these two formulas. They basically mean the same thing. They're represented using different symbols, though, and you should definitely be familiar with the symbology. So the mean is the sum of the scores divided by the number of scores in the data. Another way to think about this visually is kind of think of it as the balance point for distribution. So as you consider this graphic right here, look at the blue triangle below the gray shape there is that balance point, which we consider the mean, the point at which this distribution would be balanced. Okay, we talked about how a mean could be calculated from a frequency distribution table in the last chapter. So here we've got a frequency distribution table with scores, quiz scores of 10, 9, 8, 7, and 6 in that first column. In the second column, we've got frequencies of scores. So we've got 1 10, we've got 2 9s, we've got 4 8s, 0 7s, and 1 6. So we've got a total number of scores of 8. We see a small n there, so we're going to derive from that this is a sample, not a population. Small n equals the sum of the frequency column, which is 8. And if we wanted to calculate the mean, we could take x, each score, times its frequency. So 10 times 1, 9 times 2, 8 times 4, 7 times 0, and 6 times 1 to give us the third column, which is basically frequency times each score. We add those up, and we get 66 divided by little n. And we end up with a mean of 8.25. Okay, let's say we want to do something a little bit different here. So now we've got two distributions, right? And we want to combine them and create an overall mean for these two distributions combined. So how do we do that? Okay, so we just talked about how we would create a mean for a single distribution, right? We could take x times f for the distribution, the sum of x times f divided by little n, and little n is the total number of scores, so that'd be the sum of the frequency column. So we could do that for the first distribution on the left, we do that for the second distribution on the right, and then we could maybe take the average of the two. Would that work? Well, in this particular case, it would, only because both distributions have the same number of scores. So in the distribution on the left, we've got 2, 4, and 3, 5, and 2. That's 8, 11, 16. We've got 16 scores. And in the distribution on the right, we've also got 16 scores. We're creating a weighted mean, which means we give more weight to the distribution that has the higher number of scores. Both have equivalent number of scores, so we could just calculate the means for each of these separately, combine them, and then come up with an overall mean. Right? That would be the weighted mean. But they'd be weighted equally across these two distributions because both distributions have the same number of scores. Okay, so let's take a look at a different situation. So again, we've got two distributions here, and we want to calculate a weighted mean. So an overall mean for these, we want to combine these. So if we calculated the mean for the one on the left and the calculator on the mean for the one on the right, and then add them together and divide it by 2, would that give us the overall mean? No, it would not. Not in this case, because we have different sample sizes, these distributions. The one on the left, if you look at the frequency column, we've got 10 scores, 2 plus 6 plus 2. If you look at the one on the right, we've got 16 scores. Remember, this is a weighted mean, so we want to give more weight, or we want to apportion more weight to the distribution that has the higher number of scores. That's going to carry more weight when we combine these. So we can't just take the means of each distribution and then add them together and divide them by 2. In this case, what we're going to have to do is determine the combined sum for distribution 1, the combined sum for distribution 2, so that'd be x times f, right, for each of those, the sum of all x's for 1, the sum of all x's for 2, divided by the number of scores in 1 plus the number of scores in 2. Right? That will give us the overall mean, the weighted mean. So just talking through this, 5 times 2 plus 4 times 6 plus 3 times 2. Right? So 10 plus 24 plus 6. That would be the sum of all x's for this first distribution. Then for the second distribution, it'd be 5 times 7, 35, plus 4, plus 6, plus 6, plus 3. That would give us 39, 45, 51, 54. Then 54 plus 40 would give us 94, divided by the n from the first distribution on the left, that's 10, little n. Little n on the right is 16, so that's 10 plus 16, that's 26. So then we end up with 94 divided by 26. And that'll give us a mean of 3.6, the weighted mean. So when calculating weighted means, the further the ends grow apart, right, the bigger the difference, or the bigger the increase in the difference between the two distributions in terms of the number of scores, the more inaccurate the total mean is going to be if you don't calculate the weighted mean properly. So in this example, the distribution on the left has only 5 scores, and they're all 4, whereas the distribution on the right has 16 scores. So if we were to calculate these separately, the mean for the distribution on the left is going to be 4, and the mean for the distribution on the right is going to be 3.4. The weighted mean, though, ends up being 3.5. So if you'd like, you can pause this slide, go ahead and see if you can calculate the weighted mean. You should come up with an answer of 3.5. Okay, means are highly sensitive to changes in scores. This graphic does a nice job of illustrating that. So the further the score is from the mean when it's changed, the larger the impact on the mean. So imagine taking a block here, a blue block, and dropping it down at 2 or at 12. Right? It's going to tilt the balanced object significantly in one direction or the other. You can imagine where you'd have to pivot the mean then, the supporting triangle below the structure, in order to rebalance it. Right? And the farther away from the mean that new score, the farther the mean is going to change, or the larger the impact the mean on the mean is going to be had. Changing the value of a score changes the mean. Introducing a new score or removing a score changes the mean. So imagine pulling one of these blocks away and thinking about where you'd have to adjust the new mean to keep the structure balanced here. Imagine where you could place a block that wouldn't change the mean. Well, right on top of it, right? So if you placed a block at 7, or 2 blocks at 7, or 3 blocks at 7, that wouldn't change the mean. Adding or subtracting the constant from each score wouldn't change the mean, or change the mean by the same constant. Multiplying or dividing each score by a constant multiplies or divides the mean by that constant. So the shape does a nice job of kind of demonstrating how sensitive the mean is to changes in scores. Okay, so we talked about means. Another measure of central tendency is known as the median. The median is the midpoint of the scores in a distribution when they are listed in order from smallest to largest. So the median divides the scores into 2 groups of equal size. So if we were to attempt to locate the median in this set of 5 scores, 3, 5, 8, 10, and 11, well, the first thing you want to do is put the scores in order, and then you're going to want to identify the middle score to find the median. So the middle score in this case is 8, so the median would be 8. Well, that's easy if we have an odd number of scores. What if we have an even number of scores, an even n? Well, you do the same thing. You put the scores in order, and then you're going to average the middle pair to find the median. So in this case, we've got 6 scores, and the median would fall between the 2 middle scores, 4 and 5. So we would just take the average of 4 and 5. 4 plus 5 divided by 2 equals 4.5. Hence, the median equals 4.5. Okay, so the mean is the balance point of a distribution. Okay, it's defined by distances between scores, but it's often not the midpoint of the scores. The mean could even live at a point in which no scores actually lie, right? If the scores are very diffuse or very spread out. The median is the midpoint of a distribution, so it's defined by the number of scores, but it's often not the balance point of the scores, right? So it's directly in the middle of the set of scores. But both of these measure central tendency using 2 different concepts of the middle, right? So the mean and the median are both measures of central tendency, but they use different concepts of what the middle of a set of scores is, or what the central tendency actually is. And so what this means is that, particularly when we've got a set of scores in which there's a lot of variability, or which there are outliers or extreme scores, the mean and median can differ quite significantly in some cases. So in this particular example, we've got 1, 2, 3, 4, 5, 6 scores. 5 of them bunched right up around 2 and 3, and then one of them way out on the edge at 12, right? Which gives us a median of 2.5 and a mean of 4. So which is the more accurate descriptor of the central tendency of this set of data? Well, let's use some more natural data. So here we've got a set of people, right? A group of folks, and we want to determine the average income for this group of people. Let's say it's around $100,000, okay? So we've talked about how the mean and median can differ, right? So the median income, the middle income for this group of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people is $100,000. Now let's say we add one more individual to the group by the name of Mark Zuckerberg. 33 billion is probably an underestimate at this point. He becomes part of the group. The median remains the same, 100K, right? It's immune to the outlier, but the mean changes significantly. Now the mean has moved to 2.35 billion, right? So what's the more accurate descriptor or more accurate central tendency in this case? Well, I think we'd say it's the median, right? The median is actually giving us a better representation of the average income of this group of now 8, 9, 10, 11, 13 people with Mark Zuckerberg added, whereas the mean very much represents the average income. So it turns out that the median is actually oftentimes a better choice when we're talking about things like income or net worth or home values, particularly when there's the possibility of an outlying value or 2 or 3 or 4 in a sample. This is particularly true in cultures characterized by income disparity, that the median will generally be a more accurate approach to discussing income. So if you're ever pursuing some news regarding incomes in a given country, well, consider whether that country is one in which there exists a great deal of income disparity, and take note of whether they're giving you the mean or the median. If they're giving you the mean, it may quite misrepresent the average salary or average income. And the median is not affected by outliers. This is also true for the number of feet the average person has. So we would, if we were trying to determine the average number of feet for an average human being, we might say, well, I guess 2, right, would be the central tendency that would make the most sense. If you look down in the left corner of this figure here, there's a woman who has 0 feet, right? And there are many people that have 0 feet, and there are many people that have only 1. Right? So if we were to use a median in this case, it would yield a central tendency value of 2 feet. If we were to use a mean, it would be slightly less than 2 feet. So again, in this case, the median is probably the better choice. As if we use the mean, we would say that most people have more than the average number of feet, which would be a highly inaccurate claim to make. All right, so we've talked about the mean, we've talked about the median, and finally, the third central tendency measure is the mode. The mode is the score category that has the greatest frequency of any score in the frequency distribution. So it can be used with any scale of measurement. It corresponds to an actual score in the data. It's also possible to have more than one mode. This figure here represents a set of data in which we could rightly say that this distribution contains more than one mode. Technically speaking, the mode is the score with the highest frequency, so in this case that would be 2. But we're also looking at a peak over at 10 there, so we'd probably call this a bimodal distribution. Okay, so we've covered 3 measures of central tendency. the mean, the median, and the mode. The mean is generally considered to be the best representation of an average. That's the most commonly found central tendency measure in the scientific literature, probably. It's appropriate to choose if you can calculate the sum of all the scores and you know the value of every score. But it could be misleading in the case of extreme scores, skewed distributions, undetermined values, open-ended distributions, or when you're dealing with ordinal or nominal scales. So the median would be appropriate to choose if you've got really extreme scores, like the income example presented earlier, or the foot example. If you've got a skewed distribution, the median might be more accurate. If you've got some undetermined values there, or an open-ended distribution, or if you're using, say, ordinal scale, for example, the ranking of athletes at a track competition, then it might not be appropriate. It would not be appropriate to use the mean, but rather to use the median. And then finally, the mode. Probably the least common of these three, not very commonly found in the experimental or psychological science literature. But there are times when you might want to use the mode. It'd be appropriate to choose if you're dealing with a nominal scale variable, like college major, for example. What is the most common major? Right? It might be appropriate when dealing with a discrete variable, like a number of children. So rather than saying the average family has 2.4 children, you might use the mode and say the average family has 2 children. And it does a good job of describing the shape of a distribution, at least the peak. So it'll sometimes be referred to when you've got bimodal distributions. Finally, a couple notes regarding the relationship between distributions and central tendencies. When we've got a symmetrical distribution, we talked about symmetrical distributions before, where the highest, the scores are distributed with the highest frequency score in the middle. This is the symmetrical distribution on the left here. And then equal distributions on either side of the middle. We'll have the mean, median, and mode at the same location. Right? So the central tendency, it won't matter which measure we use for the central tendency, they'll all be the same. If we have one mode and it's in the middle and it's a standard distribution, it doesn't matter which central tendency measure we use. If we've got a bimodal distribution, then we're going to find our modes. We're going to find that we have 2 modes in different locations, and then the mean and the median in the middle. But for skewed distributions, we're going to find that the mode, the median, and the mean are not equivalent to each other. And these are the cases in which we have to determine what's the most accurate measure to properly interpret our data. Right? So in skewed distributions, the mean, influenced by extreme scores, is going to be found far toward the long tail. Right? So it's going to be the one closest to Mark Zuckerberg, or closest to the person with, say, no feet on the right distribution there. The median, in order to divide scores in half, is found toward the long tail, but not as far as the mean. Okay, it's going to be found a little bit closer to the mode, and then the mode is found near the short tail. All right, so that's chapter 3. Next chapter, we're moving on to measures of variability, chapter 4.